Hello, everybody, and welcome. Hi, welcome back to the Planet Track. We're very happy to have you. My name is Amanda Rosenbaum, and I work here at Bloomberg. And I'm going to introduce the panel session for the afternoon, using data for meaningful climate governance, opportunities, and challenges. And it's my pleasure to introduce our moderator today, Lindsey Cormack, who is the Assistant Professor of Political Science at the Stevens Institute of Technology. Please join me in giving everybody a warm welcome.
Thank you, Amanda. Thank you, Bloomberg, for hosting. And good afternoon, everyone. This is great. I'm glad that you all are here. As you can see behind me, we have a really good panel. And something that I didn't know when I was putting this together is it's really like a Captain Planet style panel. We have the oceans, we have air, we have land, we have wildlife, and so there's a lot of different substance areas that you're going to hear about how policymakers and researchers can work together. Some of the things that are going well, some of the things that are challenges, but I'm going to let each of our speakers go through their own research area to kind of highlight those sorts of things, and then we're hoping to spend a lot of time at the end for Q&A. So if you've got questions, I know there's pads and there's pens on the tables. You can write them down, and then you can ask at the end. We're going to start in a little bit different order than what you see here. It's going to be reversed. So we're going to start with Ingrid, then we're going to go on to Philip, and then we're going to end with Michael. And each one of these people is going to be able to tell you about who they are, what their background brings to the table on these questions, and I'm going to let them do that. So without further ado, Ingrid, let's do it.
Thank you. So I'm Ingrid Zabel. If you see the name of my organization, you might think that we're all about dinosaurs and saber-toothed cats, and we love those creatures. But we also have a very active program on climate change, education, and outreach, so that's why I'm here. And I'm going to be telling you or showing you some examples of the type of data needs for a small community in New York State that's taking climate action. So I'm the curator of a site called the New York State Climate Change Science Clearinghouse, and there's the URL if you want to explore it yourself. And it's a place where people can go and get data sets, data products, maps, documents, videos, webinars, all sorts of resources related to climate change in New York State. And the main audience is meant to be, I would say, local government officials or staff for towns and cities of all sizes around New York State, though I think there's a lot on the site for researchers and for teachers and students. And this site is currently supported by NYSERDA. So I wanted to introduce you to a small town in New York State, Montour Falls. Has anyone been there? Well, if you have the chance, it's a nice town in a gorgeous part of the state. It's just at the southern end of Seneca Lake. The population is only about 1,500 people. But they are highly enthusiastic, highly motivated to take climate action. And in fact, they are pursuing something called Climate Smart Community Certification. So if you don't know about that program, that's a New York State program, and the state supports communities of all sizes to take climate action. So the state provides grants and technical assistance. And as you can imagine, Montour Falls, being such a small village, they don't have a large staff. So in this process of becoming certified, they're getting assistance from Cooperative Extension and from New York's Clean Energy Communities program. And I've been involved with working with Montour Falls. And these are some of the actions that they have either completed or are working on. And if you scan this list, you can imagine that a lot of these actions require a lot of data. So I'm going to show you the example of one of them, conducting a climate vulnerability assessment, and talk about the kinds of data you might need to do that. So if you're in a community and you want to assess how vulnerable you are to climate change, you need to know the hazards you face, and you need to know what in your community might be vulnerable. So in terms of climate hazards, the key climate hazards that New York State is facing are rising temperatures, changes in precipitation patterns, extreme weather events, and sea level rise. Now, Montour Falls, being inland, away from the coast, is not feeling sea level rise directly, but it is experiencing those other three climate hazards. And then you need to know what is vulnerable. So broadly speaking, in your community, people could be vulnerable, built infrastructure, and ecosystems could be vulnerable. And this is a map, a nice map from the New York State Department of Health about people. So it's a map of vulnerability of elderly people, so people over age 65, especially those living alone. And they can be vulnerable to flooding and especially extreme heat. And you see here in Schuyler County, where Montour Falls is located, they're right about there, they have the highest elderly vulnerability in their county. So they have a lot of older people living in their village. So this is a data set you can find on the Clearinghouse that could address that, give you some information about extreme heat. So let me walk you through what this graph is showing. So this is plotting a time series plot, counts of days per year with a maximum temperature above 90 degrees Fahrenheit for Schuyler County, where Montour Falls is located. So on the vertical axis, you have counts of days. On the horizontal axis, you have time in years. So it's going from about 1950 to the end of this century. So on this plot, you have both historical observations, and that's what the black dots are. So those are the number of days above 90 in each of those years. And then you have these projections, the pink and blue regions. And the pink, these are results of 32 different climate models. And the pink and blue just sort of denote the higher results and lower results. And this line in the middle is the mean modeled result for each year. Now, of course, future climate depends on the choices we make. So we can choose to keep emitting greenhouse gases as we've been doing. We can choose to cut them somewhat. We can choose to cut them a lot. So that's always, that kind of choice and that kind of scenario is an input to climate models. So this particular plot I'm showing you has a scenario called RCP 4.5. RCP stands for Representative Concentration Pathway. So that's a pathway where greenhouse gas emissions peak around the middle of the century, I think around the year 2040, and then they decline. So we do a pretty good job at cutting greenhouse gases. And in that scenario, in Schuyler County, by the end of the century, the mean level is they can expect about 21 more days per year of extreme heat, of temperatures above 90. So let me show you another scenario. Same data, but in this case, we don't do a good job of cutting emissions, just business as usual. We keep on emitting gases into the atmosphere. And in this case, by the end of the century, they can expect about, the mean result is 49 more days per year with temperatures above 90. So these data are pretty sobering, but you can see how they would be important to a community to plan. If that's where we're headed, how can we keep people safe in extreme heat? It also can be motivating to say, let's not do this. Let's make choices, other choices, so we don't heat up our atmosphere this much. All right, there are some challenges of data availability. This is a map of FEMA flood zone maps. And actually what you're not seeing here, the way it's zoomed out, you're not seeing FEMA flood zones. You're only seeing where digital data are available. So if it's pink, it means there are FEMA digital flood maps available. If it's white, like where Montour Falls is, there are no digitized FEMA flood maps. And in fact, for Montour Falls, the most recent FEMA flood map they have is from 1983, and it's an analog map. So even without climate change, that's really an old map, and things have changed in their community that might have changed their flood risk. But ideally, of course, you'd want to incorporate climate change in thinking about future flood risks. And in the interest of time, I'm going to just sort of skip through this, but just say there are tools out there people have developed to look at future flood risks. And my last slide, just want to show you a few examples of, on the sort of vulnerable asset side, a few examples of data. So on the Clearinghouse, you can find data about trout streams. So trout fishing tourism is a big industry in New York State, and trout are very vulnerable to climate change because they're a cold water species. You can find rare plant and animal data. You can find land cover data. So these are the types of data that a town, even a tiny village, would need to look at and assess how vulnerable they are. Thank you.
I'm Philip Orton, and I'm one of the people who make those flood risk maps, among other things. I'm a physical oceanographer at Stevens Institute of Technology across the river in Hoboken. I actually live uptown at 93rd Street, so a pretty short commute for me. Really excited to be here. Thank you, Lindsey. We're both at Stevens Institute, actually, Lindsey and I. So this is a map showing New York City's flood problem. This is about a once per year flood. This is Rockaway Peninsula, one low-lying intersection. So we don't have it as bad as Miami or Norfolk, these places that are really low-lying, that are starting to get flooding just from tides, sunny day flooding. We have a few corners that have sunny day flooding, but this was after a nor'easter or a week weak nor'easter with really big tidal ranges or spring tides. So bad coincidence of big tides and a small nor'easter. So this is salt water, and it destroys a lot of cars, and so that's our problem with flooding right now. Globally, though, Munich Re estimates that in the past 40 years, there was over $1 trillion of flood damages. So this is a global problem, and over 200,000 people died. Many of those are in places like Bangladesh, deltas. It's a problem that impacts poorer and lower-lying delta cities and populations more than a place like New York City, in spite of our bad luck with Hurricane Sandy 7 years ago. So I'm a member of the New York City Panel on Climate Change. We put out reports 3 times. It's about 20 scientists and really interactive with New York City. So New York City has a lot of resources to throw at this problem, the broader problem of climate change. My contribution in these reports, we just had one come out in 2019. You can go online and pretty easily find it. And one of the chapters was coastal flooding, so that's my topic area. So I'm a physical oceanographer or ocean engineer, depending on how you look at it. And my main tool is to use computer simulations of water movement, so hydrodynamics. And so we simulate floods, we simulate thousands of different storms and floods. We add in sea level rise into the model, raise up the ocean level in the model, and we can do a pretty good job of quantifying flooding. But when you want to, represent risk, that's a tough thing. These reports have like 2 maps of flood risk, and that's all that people, that's all that the average stakeholder is going to digest. It's the 100-year flood zone, and it's going to get bigger with sea level rise. And so that's the kind of simplistic information we put out there based on this modeling that we do, computational modeling, and based on a lot of historical data. It's not just trusting the models. But then one thing that I did that's more complex that I think starts to get at, the kind of data that we have and what we can do with it is this is called a DAP map. It's a flood mapper. Climate Central is a real good organization that has a flood mapper called Surging Seas that tells you how high tides will get higher with sea level rise. This mapper allows you to look at not just sea level rise, but also storm. Instead of high tide, it's got storm scenarios from a 5-year. So these are basically inverse probabilities, right? The 5-year flood's a 1 in 5 chance every year. The 100-year flood's a 1 in 100 chance, 1% chance every year. So we've got probabilistic data of water level or flood area, really, is what you see. Here's the water depths above ground. It's not a pretty picture, of course. This is the 1,000-year flood. I don't know why I was so cruel to Jamaica Bay, New York. This is JFK Airport. But for this case, I showed the 1,000-year flood on present-day sea level. But you can choose different sea levels, different probability of flood. And then the innovation is that it's not just a sea level rise mapper, it's an adaptation mapper. So in our model, we changed the landscape. And we looked at different historic landscapes, like the 1800s. There's actually good enough map data to make an estuary model, a flood model for the 1800s. We're doing that for the whole New York City, actually, for an NSF project now. But then there's also some adaptation choices, like undo the shipping dredge shipping channel, add wetlands, things like that. So we can quantify these different things in the model. So the type of data that we have, it's dynamic model based, so there's a lot of things that aren't even shown here, but this actually shows a lot more than most mappers and New York City Panel on Climate Change reports show. And somebody can dig into this and explore it. And they can see benefit cost analyses, impact GIS data on impacts and damages, et cetera. You can even, there's even a play button, which isn't really in the, I wish it showed it here, a play button kind of thing on a separate page that shows an animation of the flood. So it shows the water and its time dependence. So there's lots of dimensions to this data. And I don't really work enough with data science and think enough about how to better portray it. We work with CSUN on this, so this was pretty nice, and that was one collaboration. But we can do even more. And also, it's a lot of computation. This was, many months of supercomputer time to do all these computations of the water movement. So those are 2 big problems in my field and reasons why it's good for me to be here today. And then the other thing we have is forecast. So that was flood risk, looking at present decade, future decades, the flood chance per year, probability per year. But we also forecast for the next 4 days. And so this is also something that's really helpful globally, and hopefully will get better and better, is forecasting. So NOAA will give you forecasts, but we also have an academic version, and we're kind of pushing the leading edge of how to do forecasting. And these forecasts, much like what I just showed, they're also probabilistic. They're run on an ensemble. So at all these locations up the East Coast, you can look at the flood forecast, you can get emails sent to you, and it provides something more complicated than what NOAA typically portrays. So it's a little more better for the water user or the boater or something. So these are the tides and the tide variation. You've got red dots are observations. The magenta is the prediction for 4 days into the future. And again, it's probabilistic. So we run 100 different weather models with all the uncertainties, the European model, the American model, et cetera. It's all thrown in there. You get a probability distribution of a result. So these are 90% confidence intervals. So again, so I don't want to dwell on this too long, but this is definitely our bread and butter kind of output, is this probabilistic water level data. Sometimes it's for years into the future or days into the future. And so it's got lots of dimensions of information that's available. So the big struggles that I have in my field are we need massive computation to simulate all these possible floods with this time-dependent model that we use. And maybe even adding in adaptation and climate change into our, and so many different scenarios. But we are exploring cloud computing and machine learning as ways to reduce that computational burden. And then we need innovative web tools or other sharing architectures, and that's something I'm really interested in hearing about if people want to talk about that today. We've done some of that with Columbia with the mapper that I showed, the AdaptMap mapper. And lastly, I just haven't been doing enough of this, so I think I'm really excited to be here today and learn more. So thank you.
And now we'll hear from Michael.
Hi, I'm Michael Mandel. I'm an associate professor at Brooklyn College in computer science. I'm sort of coming from the other side, the machine learning side, and I'm a little bit new to the environmental side of things. But I have this new project that's been going for about a year. So it's called, well, the title of my talk is Navigating the New Arctic with Ecoacoustics. So the basis of this project is a couple of problems. The first problem, well, actually, so the first problem is that Arctic boreal forests are warming. This is a picture. I was just up there a couple weeks ago. It's an awesome place to go. I would highly recommend it. But they're warming at 2 to 3 times the global average. And so this causes large interannual swings in meteorological conditions. The snow and ice cover is decreasing in some areas, it's increasing in other areas, it's stable in some, and it's relied upon by migratory songbirds and waterfowl for reproduction. The second problem is that in the same area, oil and gas exploration may be affecting caribou migration. Caribou, which is a wild version of a reindeer, migrate about 1,000 miles annually. There's different herds. And oil and gas infrastructure changes the migration routes. And oil and gas infrastructure, which is big in Alaska, in Prudhoe Bay, also involves a lot of vehicle traffic. So land vehicles, boats, and aircraft. Their usage is all increasing. And also there's an area of the Arctic National Wildlife Refuge that was open to oil and gas drilling in 2017. It hasn't started yet. Exploration hasn't started yet. This is another problem, is that this is having an effect on these caribou, and they're native Alaskans that depend for their subsistence on hunting caribou to a large extent. So this is affecting them as well. So the scientific questions that we're investigating is how is climate change affecting songbird and waterfowl phenology, which is a word that was new to me, and it's basically how does it affect their migration timing. And the second question is how is human-generated noise affecting caribou phenology? How are we going to answer that? Our solution is ecoacoustic monitoring. So the idea is we've set up these autonomous audio recording units deployed throughout the summer. We just finished our first season. These are locations that we recorded at. Over the 5 years of the project, we're expecting to get about 400 terabytes of recordings, which if you listen to it end to end would be 50 years of audio, and also camera traps to count the caribou because they don't make as much noise. So if I zoom in, this is a better view of those recording locations. So there's this is the Arctic National Wildlife Refuge. This up here is the 1002 region that's going to be open for oil and gas exploration. These are the caribou, the places we're interested in the caribou, and these transects here are where we're interested in the bird migration routes. And so this is a picture of one of our locations. This is the audio recorder. This is the camera trap. And this is the tundra. So these are the kinds of pictures that we get from the camera traps. So the idea for the caribou side of the project is to, in these pictures, find the caribou. So let's play a little game. Does anyone see a caribou? There's a couple of birds. How about here? Yeah. See a caribou? Okay. How about here? Yes. There's a tiny one right there. So we need to see that. How about this one? Yeah. And how about this one? So apparently bears like to scratch themselves on those the posts that are. So this is a camera that's been knocked over, and we have a bear. So my background in all this is, as I said, the machine learning, but specifically applied to audio. So my part of the project is to take these 400 terabytes of recordings and try to figure out what's happening in the sound. So can we answer these scientific questions from these audio recordings? We have some preliminary results by my collaborators. So in this case, they deployed these same recording units at 5 sites for 5 years. And they were using this for the songbird aspect of the project. And they found that these are their acoustically derived dates of songbird arrival on their migration. And these are those dates observed by people on the ground. They found that they agreed quite well. So we're using this for these latitudinal transects, and we're using fancier models. And for the human-generated noise in caribou, another project of a collaborative of mine, they deployed these autonomous recording units at 20 sites in one summer and identified these noise-free intervals. So red means that the mean noise-free interval was 0.1 to 1.2 hours, and blue means around 20 hours. So these sites were relatively noise-free. These sites where there are airports for oil and gas exploration were more noisy. So for this, we're going to monitor these same things and automate expand to more sounds, more sound classes. And this was all done manually, so we're going to do it automatically. So in terms of resources, I just wanted to mention a few things. This DCASE challenge, the detection and classification of acoustic scenes and events, it's coming to New York in October. So if you're interested in this sort of thing, it's a challenge. So they have standard data sets and metrics and baselines that you can start from. But it's also a workshop, so I'm on the one of the program chairs for this, so it should be a good 2-day workshop at the end of October. There's different tasks in the challenge in this sort of bake-off model. Acoustic scene classification, audio tagging, sound event localization, urban sound tagging, and in the past they've done bird detection. There's also other ones. The BirdClef is an annual one that does bird species recognition in isolated recordings and in soundscape recordings. So just here's some examples. So the challenges themselves have all closed already, but it'll be happening again next year. So stay tuned for that. And we used, so we took one of these models, the winner from the 2017 bird detection challenge, and ran it on one of our locations, the location that had the smallest noise-free interval in that map. And so I'm plotting here, these are days, the x-axis is days, the y-axis is a predicted probability of either bird presence with the blue line, also bird presence with the green line, or engine-like noises with the red line. And so we were able to analyze this month's worth of data and make some predictions using these models. So the idea, this is just sort of the first step, but we're going to scale this up to all of the sites, all of the recordings that are coming in, compare them with the camera trap data that we have, and do all sorts of other ground truthing of it. But this is the idea, to utilize audio recordings to answer interesting scientific questions in the Arctic. And if you're interested, yeah, so October 25th, 26th at NYU Brooklyn. So just in summary, audio can answer many timely scientific questions about the natural world, especially when combined with this machine listening idea. There's a lot of resources out there, code, data, and tasks. And one challenge that we're facing is providing open data, but also protecting game like the caribou from commercial hunting. So we need to protect them for the subsistence hunters. Thank you.
So before we get into questions from you all, I think anyone that I'm seeing in the audience has like an interest in learning more on this. Can you guys tell me some of the like accessible online data portals that you're like, yes, this is where you get good data for X, like things that you use in your daily practice? Ingrid, do you have some? Well, yours.
So, I mean, there's certainly some similar sort of national sites like the U.S. Climate Resilience Toolkit. And associated with that is a tool called the Climate Explorer. And remember I showed you that graph of extreme heat for Schuyler County? So our resources are focused in New York State. But if you go to the Climate Explorer, you can find for any county in the U.S. climate historical data, climate projections of all different types. So that's a great site. Michael and Philip, what are the ones we use?
Well, for us, the DCASE community provides a lot of these resources. It's a big hub of that sort of thing. So that's the first place I go.
Yeah, I'd say the most common place I look for data is from the federal government or, so NOAA, National Ocean Atmosphere Administration. But I have pretty specialized needs, I guess, for these like weather data sets and things, so, yep.
Amanda or Molly, do we have microphones for the audience? Or do we have, you have one, yeah? So we can open this up. If you all want to start with your questions, I'll let you guys jump in. If not, I have some that are burning. Is there anyone here who has something that they want to ask our panelists about? Do it.
I'm going to be very honest, and everybody here could hate me for it. I'm not a believer that climate change is man-made. Because things like from the federal government have come out and said, just like the other day, that sea levels were 52 feet higher at one point in Earth's history. And the NOAA also says that Earth naturally heats every few years, or every few thousand years, and that we started the last cycle in about the 1850s. So I was just wondering, like, what your response is to the federal government or these agencies saying, hey, look, maybe we can't stop this. You know, we're destined for it. There's going to be another ice age. Earth's going to heat up. So I'm just wondering what your response is to that kind of segment, or my thinking, rather.
Well, I can address some of that. So certainly in Earth's history, the climate has changed many times. From extreme cold to extreme hot. I think what's different now is the rate. So if you look over the last 800,000 years, there have been these cycles of glacial and interglacial, so cold and warm periods. And there have been changes on the order of, a few degrees Fahrenheit in tens of thousands of years. Now we're seeing changes on the order of a few degrees Fahrenheit. I think it's now been, in the last 100, 150 years, something like 1.8 degrees Fahrenheit change over just a few hundred years. So you really have to put in sort of the perspective of the geological timescale. There's nothing like the rapid rate of change that's happening now. But you're right, Earth's climate has changed many times in the past. Yep.
Yeah, and I'd say I'd agree with what you just said in that it's not thousands of years. I mean, it's tens of thousands of years. It's ice ages where we have similar size climate changes as what we're expecting to get this century. And it's happening in a century and not in 1,000 years. So it's not, human, populations have grown in the Holocene and in a period of time with over 10,000 years where there's been a very stable climate. So we're definitely experimenting with something that that hasn't happened in that period of time that humanity's grown. But climate science is really cool, and it's incredibly fascinating. And, when she says something like, oh, we know about millions of years, you can be skeptical, but, it's like this incredible, I think you should just dig deeper into it. It's really fascinating, and there's so many different types of science that go into what she said. And I think, and it's really solid. I mean, trust the climate scientists a little more.
Thank you for your presentations. They were very informative. Something that came to my mind was, like you mentioned, the rate of change of climate, which is also, quickening the pace of certain deteriorations in the environment. Do you feel, in your research, that the goalpost keeps moving with, how policies change and that the impact that has on the environment, plus also the rate at which the climate is changing. So what you're studying today, may not be on the mark a few years from now. And I'm just a student of data science, so I'm just trying to understand the things you have to put into place and into perspective when you start out with research. Makes sense.
What do you mean when you say the goalposts keep moving?
So one is the rate at which the climate changes, right? So you can study an environment based on what the climate looks like right now and what you think it's going to look like a few years in the future. The other is also the rate at which policies change or ecosystems change or our dependence on the ecosystem changes, right? How we adapt to those things. So that's what I mean by goalpost change. Does that make sense?
Well, climate's already, in maybe 1980s, there was prediction of how much doubling of CO2 would change climate, and we're already a good part of the way into that. So that's one way things are evolving as we're studying it, and sometimes it can make you want to give up because there's already so much baked in. But I think there's still a lot. As the plots in the first presentation showed, if you have a medium RCP 4.5, a medium amount of carbon emissions this century, the outcomes are really different than if you have business as usual and a large amount of emissions. So that's a big motivating factor. As I'm thinking beyond my own life, I'm thinking to 2080 and 2100, where I feel like the world will have catastrophic problems that don't have to exist if we could avoid all those emissions.
I think just for my project, it's sort of a bit more localized, but we're trying to figure out what exactly are the effects for these particular problems that are apparent. And so I think we're not looking 100 years out, we're looking maybe 10 years out, but trying to be able to say something meaningful about a particular ecosystem or particular relationship between a community and its environment. So I think at that scale, we can at least study it and hope to have some solutions.
I hadn't thought about it the way you posed your question, but the way I think about it is, yes, we've known about the basic physics and chemistry of climate change since the late 19th century. We've known, as Philip said, about the changes happening since the 80s. I suppose one could always argue that it's too late. We should have been decarbonizing our energy systems a long time ago, but I'm not ready to give up. It's not too late. It's too late, but we can still keep making changes, doing the research, but really taking action.
Max Livingston. I don't know much about climate science or politics, but I do work a lot with probabilistic forecasting. And so I'm curious, sort of, when you think about these 100-year forecasts and trying to communicate those to New York City politicians, how do you convert these, these confidence intervals into something that politicians can understand and sort of work with? And how do you convince them that something that has a 5% chance of happening, what that means, or how to get them to take action?
Yeah, and before you guys answer, I kind of want to ask something about this too. New York is interesting in the sense that we have a lot of resources and the people who are working on these problems are really into these problems. But what about smaller communities where you're having to convince policymakers or stakeholders where they're just it's not at the top of their list of interests? How do you do these sorts of things in your work?
So I can comment just from working with Montour Falls. I think if you can connect it to economic development and the economic developments about taking climate action or economic benefits of taking climate action, that's powerful. I also think if you can talk to people when there's been an extreme weather event, that's highly motivating. So for Montour Falls last year in August of 2018, there was really terrible flooding in the Finger Lakes, and that's a big part, and they acknowledge this, that's a big part of what got them going.
New York City understands these, New York City has a lot of good scientists and engineers working for it, and so they do understand a 100-year flood, or that it has 1% chance of happening every year. One thing that we did there that is a very, very hype, for the average person, looking at a 100-year flood map and saying it'll get worse, it's kind of whoa, it's already bad, So it doesn't connect that well, actually, and we were adding the sea level rise on top of the 100-year flood in 2015's report. But in 2019's report, New York City said, and somehow in our conversation around the work with monthly meetings with the city, we decided to have tidal flood maps. And the monthly tidal flood was sort of a new thing that I came up with. And now we had a map this time in 2019 that showed the monthly tidal flood, which is hardly hitting anything right now, and it's every month. There's only a few places, you know, in the city, but how that will advance with sea level rise in coming decades. And so you can see the advancement of that guaranteed flooding instead of an extreme event that actually has a good chance of not happening in a given decade. So. And so New York City is using it for zoning. There's some neighborhoods in New York City that are really low-lying, former wetland areas that got landfilled, that are now zoned. It's an experimental new zoning where they won't have any more density added to the neighborhood. They're not saying retreat now, although they could in the future, encourage people to have buyouts. And then for city planning, they're trying to use it for zoning. These actual maps that we create for zoning and for regulating new buildings to have to be, right now I think it's just city buildings, but they have to be above the 100-year flood affected elevation.
So I have a quick question. The work you guys are doing is all great, but it's very isolated. So Boston is flooding, New Jersey's flooding, Virginia's flooding, New York could be flooding. What are we all doing collectively to put all of this manpower, brain power together to solve it?
We try to, help the federal government with their, learn more, and so even if it's a localized study, it can be influential. I am working with the U.S. Geological Survey right now to try to take this monthly flood mapping and sea level rise impact capability to a national level. But definitely a good question. Often it's it's hard for us to provide things that are useful to everyone. So that's a challenge. And that's one of the reasons why it's big data. If you do think of it as big data and start trying to scale up the work that we do with cloud computing or something, then you could create something that's nationwide. And so it is an important thing for us to think about.
I think in terms of the tools that we're using, there's several projects around the world doing, using similar tools. We're exchanging technologies, we're exchanging ways of classifying sound, analyzing sound, and using it for these applications. There's a big project at NYU, BirdVox, that's doing this for New York State. So I think in terms of that, in terms of monitoring, in terms of the acoustic environment, it's a little easier to spread things around as long as you can stick out a microphone and collect some sound.
I'll mention that in addition to curating the New York Climate Change Science Clearinghouse, I curate one for Massachusetts as well, which is based off the same framework, so we share data. But that's also sort of still specific to one state, so maybe doesn't get at your question. I'm not a climatologist, but Art DiGaetano, who I've worked with at Cornell as head of the Northeast Regional Climate Center, has said that if you look at the Northeast, we might think of the climate in New York City being quite different from the climate, let's say, in Maine, but on a global scale, they're not really that different. So there's a lot of information and data and maybe solutions that can be shared, certainly regionally. But I think there also are a lot of good federal resources out there.
But I think this question is good. It speaks to like a collective action problem. Like this is a collective action that everyone needs to take. But what I think it seems that your research indicates is only certain entities or stakeholders are willing to do it. And so you can't expect like a big federal program if we don't have federal consensus that it's a priority. And so when you have states that are willing to lead, like New York or Massachusetts or California, that's something that like allows models then to be used in other areas. But it's a really good question. It's a bigger problem and a lot of small solutions that hopefully chink away at getting to the final solution of it. Who else? You got one here?
Yeah, so one thing that I notice when I hear reactions from like non-quantitative lay people a lot is the way you guys report a lot of the results, or you guys being, the scientific community, is in terms of averages, and for most people when they hear like 2-degree level warming or whatever, they're like, okay, when I go home and turn on my air conditioner, I raise my apartment temperature by like 6 degrees in 20 minutes, who cares? And I think there's a issue where non-quantitative people don't really understand the difference between averages and variance, and how, and what you guys are talking about with like 100-year floods, 1,000-year floods is, that's about what most people consider to be outliers and be like, throw that away, that's, an outlier. But actually that's the important part of the data. Like, do you guys look into, like, how do you guys think about how to make your conclusions more intuitive for the public that doesn't really maybe understand statistics?
It's a constant thing to strive for. I mean, probabilistic information is confusing to people. So, and that's one thing I think it was a victory to have monthly tidal flooding, because it's something somebody can walk over and see. A week ago when there was there was a king tide. So they'd have more of a sense of its reality, whereas the 100-year flood maps were so imaginary and hypothetical, even though Sandy had hit. So no, that's a great challenge. I mean, that really is, and I think we definitely work hard to try to make things more tangible, but it's real hard. I mean, education and people don't understand probabilistic information, and so you have to find a way to make it simpler and present simpler. And so if we have a mapper like the mapper I showed, that's the kind of thing I do want to try to understand, is how to have it be simple on the surface and complex underneath for people who want to dig deeper, and have it be useful for different types of users.
That is a difficult challenge, and I think a lot of people don't understand the difference between climate and weather. And you can think of, some people define climate as an average, say, over at least 30 years of the weather in some location. But that doesn't encompass everything, because of course you want to include the extremes as well. So maybe communicating more about climate and weather, trying to teach people what the differences of those. Using analogies I found is useful. So there's a nice analogy about climate change and hurricanes, that the atmosphere is, with climate change, is sort of like the atmosphere on steroids. And thinking of the analogy of a baseball player, you could think of a baseball, say a Major League Baseball player who hits a lot of home runs, and then maybe he started taking steroids, and he hit more home runs. And you can't attribute any one of those home runs to the fact that he's taking steroids, but you can say he's hitting more because he's taking steroids. So using those kind of analogies can sometimes be useful in communicating about climate change. Yeah, that question of why do we care about 2 degrees, it sounds like such a small number. I have not found a good solution for that yet. So if anyone thinks of one, let me know.
Hi, I wanted to touch a bit on your point about economic incentives for communities to really care about climate change. A lot of industries don't, they profit from not caring about climate change, and that's an active decision that a lot of them make. But you mentioned also, Philip, about working with Munich Re, and insurance as an industry is one that really benefits from staving off the effects of climate change. Is there any are there any just generally large applications of your research that really applies to benefiting industries, so insurance for reconstruction costs, for example, or any other industries that really could benefit from the application of your research?
I'm not sure how to answer that. I don't have any knowledge of direct applications, but let me think about that while you're answering.
With the New York City Panel on Climate Change, a couple years ago we had a meeting with them, and they're moving beyond the research we did, and they're trying to get FEMA to, as a pilot, start putting sea level rise and climate change into their standard flood map, not to provide it for insurance, but to provide it for zoning and just for for those kinds of applications. And so the room was full of people from insurance, from many parts of New York City, with all differing levels of information need, from simplistic to really detailed and complex. So that was a real learning experience. So I mean, it can go toward helping industry. A bunch of my colleagues left and formed a company called Jupiter, which provides, which aims to provide climate and weather risk data to companies. So it can be more of a business model to provide data to business. But definitely the science that's being learned is at some level being used to help inform business or for insurance companies.
I mean, so this is not direct application of my research, but I mean, just an interesting economic consequence of this. In Alaska, there are villages on the coastal plain where they would receive revenues from oil and gas exploration that are in favor of the drilling, native villages. There are other native villages that rely on the caribou, and the caribou would be disrupted on some other part of their migration by the exploration, and they're not in favor of the oil and gas exploration. But you can sort of see the direct economic interests of the different parties based on how they feel about this, what's happening. what they want to see.
Okay, I think we have time for one more question in the back.
Yeah, thank you. Great presentations. I had a question about the first presentation that you made where you had a graph showing a forecast of temperature and I guess an extreme number of days of extreme temperature. And I had two questions about that. The first one is it seemed like the left side that showed black dots, which was the reality, and then the two colored lines were a forecast. It just seemed like both lines were significantly above. The forecast seemed to err on the side of much higher temperature than what was actually realized. So that was my first question. Was that true or not? And the second one, I was curious if you tried to maybe say, you made a very good point. Like this assumes we don't do anything, but we may have some choices of what we could do. And if, for instance, we increased our resilience in this town, maybe this particular area with very vulnerable populations to high extreme in temperature might not be as vulnerable. Or if we did this behavioral change and we reran our model, maybe the extremes would be much lower. I thought that is that something that you looked at, or?
Yeah, so the behavioral change, the choices I was talking about was really directly about greenhouse gas emissions, because that's what's input to those models. So we can make the choice to change our energy systems, the way we heat and cool buildings, change our transportation systems so we're emitting fewer greenhouse gases that are warming the atmosphere. And then in the future, we're less likely to have those extreme number of extreme heat days.
And on entire New York State?
Well, it's a global problem, really. Yeah, I mean, everyone has to participate. So we do what we can. I think New York is actually pretty forward-thinking on that. Yep.
With that, thank you all for being here. Thank you for your questions, and please join me in congratulating and thanking our panelists.